students, we are moving on to the module 2 of the course Solid State Devices of KTU. We need to remember all the basic concepts that we have learned in module 1 regarding the carriers in semiconductors. The basic concepts which helped us find the concentration of electrons and holes in semiconductors. In this video, we will be seeing the basics of carrier transport in semiconductor. Carrier transport. Why we are interested in carrier transport? This is for understanding how current is flowing in a semiconductor. In order to understand current in a semiconductor, we need not only the knowledge of carrier concentration that we had seen in first module, we must also be able to take into account the collisions of charge carriers with the lattice or the atoms and also with the impurities inside the semiconductor. This introduces a new term called mobility of carriers. That in general can be called or termed as carrier transport. Generally, there are two regimes of transport, which are low field transport and high field transport. Now let's take an example of a semiconductor wafer, say a silicon wafer, a cube as shown in the figure is doped with N-type impurities. So we are having an N-type semiconductor in our hand. Since it's an N-type semiconductor, the majority carriers are electrons. And as you see in the figure, it is not connected to any external voltage source. So there is no field applied to it. Since there is no field applied to it, there will not be any current. But don't think that the free electrons within the semiconductor wafer are sitting idle. It is moving within the semiconductor wafer. But while they move, they collide and their direction changes. This motion is due to the thermal energy it is having. Suppose we are keeping it in a room temperature. So that temperature is equipping the electron to move even when there is no external field applied to it. But the nature of this movement is such a way that electron is not moving from a point A to a different point B. Because of this random movement, the electron comes back to the same position. So in effect, there will be no net motion. Though it is moving around, it's coming back to the starting point. Don't think that these collisions of electrons during the thermal motion is because an electron is hitting another electron in the path. It is not the case. The electrons are not hitting other free electrons. But these collisions are happening with the vibrating atoms. As you see in the picture, where atoms are connected with springs in between. As you know, if it is connected with a spring, it can move. Don't think that in reality there is a spring inside, but just to understand that the atoms are not fixed, I have added springs in between. So the atoms can move in all directions. and that makes the atoms as vibrating atoms, and they are also known as phonons. Another possibility of collision of these electrons are collision with the ionized impurities. What do you mean by ionized impurities? You know that you are doping a semiconductor. In our case, we had doped with pentavalent impurities so that we get an N-type semiconductor. So while we dope, as seen in the figure, a pentavalent impurity arsenic is being used for doping. It gives out the fifth electron of its outer orbit as free electron. When it releases this free electron, it becomes a positively charged ion. If it was a trivalent impurity, an acceptor impurity, it will be accepting an electron and becomes a negatively charged ion, which is denoted as Nd plus. The positively charged ions are normally denoted by Nd plus, and the negatively charged acceptor ions are denoted by the term Na minus. These ionized impurities is also taking part in the collisions with the electrons. So as I had mentioned earlier, while the electrons are moving without any external field applied, the thermal motion, it collides with vibrating atoms and ionized impurities. This will scatter the electrons moving in the wafer, or this movement is called scattering of electrons. That was the case when there was no electric field applied to the semiconductor. Now, suppose an electric field is applied to the same N-type semiconductor that we have. A battery is being connected. So there will be an electric field now connected to the semiconductor. Electrons will move in the direction opposite to the direction of the electric field. That is the convention that we follow. Now what happens? Along with the scattering of the electron, due to this applied field, electrons can move from a point A to point B. So this will constitute a current flow. Earlier, without the electric field, there was no net current, though electrons were moving, colliding and moving, but coming back to the same position. But after an electric field is being applied, it gets the capacity to move from one point to another. So the electrons have gained mobility now. Now we will see the term mobility in detail. Before we derive an expression for mobility, we will introduce few assumptions or few terminologies that we use. First one is tau, which is the mean time between collision. There will be n number of collisions. Tau is the mean time between collision. Suppose first collision it took tau 1, the second collision it is taking tau 2, and so on and so forth. You are averaging it, and tau is the mean time between collision. V is the velocity of electron from one collision to another. This movement or velocity attained by the electron is due to two things: the thermal collision and also due to the field applied. The velocity attained by the electron due to the applied electric field is known as drift velocity. Now we will make use of few basic knowledge that we have. Velocity is equal to acceleration into time, or in other words, velocity by time is acceleration. A is the acceleration of electron between collision. Now another basic equation we are going to use, which is force is equal to mass into acceleration, or in other words, acceleration can be written as force by mass. Now what is the force that is acting in this case? In this case, it is the applied electric field which is giving the force. That force can be mathematically represented as Q into F, if Q is the charge. And from the module 1, we have already understood the concept of effective mass. So here we take the effective mass Mn star, so that all the other quantum concepts are being incorporated into the mass. Now substituting these values into our basic equation of velocity, which is equal to acceleration into time, we have velocity is equal to Qf, which is the force, divided by Mn star, which is the effective mass of the electron, into time tau. Now we just rearrange this expression by repositioning the positions of tau and f. So now we have an equation V is equal to Q tau by Mn star into F, and the term inside the bracket, which is Q tau by Mn star, is represented by mu n in case of electrons, which is known as the mobility of electrons. As you already know, whatever is applicable, whatever concepts that we discuss with electrons is applicable with holes. So we could relate this equation to that of the mobility of holes, which will be represented by mu p. In place of n, you will be putting p, is equal to Q tau by mp star. So that is the mobility of holes. This is mobility of electrons, which is seen in the screen. So generally we could write the equation for the velocity V as mu into F. F is the electric field applied, mu is the mobility, and V is the velocity. So velocity is mobility times the electric field applied. And mu n is equal to Q tau by Mn star. Tau is the mean time between collision. The unit of mobility is centimeter square volt raised to minus 1 second raised to minus 1, or centimeter square per volt per second. This is because field is volt per centimeter and velocity is centimeter per second. Now if we plot a graph between the velocity and the applied electric field, we get a graph as shown in the part A. We see that as the electric field is increased, velocity of the electron also increases linearly. And also we can tell that the slope of this curve is the mobility. So as we increase the electric field, there will be more mobility or more velocity for the electrons. This is for a particular material. Say the material that we are using is the silicon. If some other material is that, there will be a different curve. On the B segment of the figure, we see that after a particular time of increase in electric field, the velocity tends to saturate, so that the curve now flattens. The figure shows the curve for electrons and holes. So what we should understand is that until a particular point, as we increase the electric field, velocity of the carrier increases. But after a particular point, it saturates. The transport, carrier transport until the saturation, or on the initial part where while we increase the field, velocity also increases. That part is known as low field transport. And the transport after the saturation, or even when we increase the electric field, there is no linear change in velocity. That segment, that part of transport, carrier transport, is known as I field transport. So in a nutshell, we could say that a carrier go as fast as we like just by increasing the electric field until the saturation is reached. So that is regarding the basics of mobility. Now there are some dependencies of this mobility to other factors. One is temperature. Variation of mobility with temperature is that on lower temperature, the mobility is basically depending on impurity scattering or scattering due to ionized impurities. As we increase the temperature, the lattice scattering or the vibrating atoms controls the mobility. It's a common sense. As we increase the temperature, the atoms will vibrate more. So on lower temperature, the mobility is depending on the impurity scattering, and at higher temperature, it is depending on the lattice scattering or the scattering due to vibrating atoms or phonons. To summarize this effect, as the temperature increases, since the thermal agitation of the lattice becomes greater, scattering from crystal defects or the ionized impurities is more prominent. The dependencies in number is like T, temperature raised to minus 3/2 for lattice scattering, and T, temperature raised to 3/2 for impurity scattering, which is evident in the figure that we had seen earlier. I will show the picture once again. On lower temperatures, it is due to impurity scattering, which is T raised to 3/2. In case of higher temperature, it is T raised to minus 3/2. Now we will see what is the effect of variation in impurity concentration or the doping. As you know, if we have more concentration of impurities, even in the higher temperature, it will be affecting the mobility. Earlier, if it is only moderately dropped, impurities are affecting the mobility during the lower temperatures. On higher temperature, it is purely due to lattice scattering. But if we are having heavily doped semiconductors, then even at higher temperatures, the impurity scattering is also evident. As a summary, the mobility of the carriers within the semiconductor depends on temperature and doping, too, along with the applied electric field. With this, we will stop our discussion on this carrier transport topic. In our coming videos, we will be discussing points like Hall effect, diffusion, Einstein relation, Poisson equation, and continuity equation. The movement of carriers due to the application of electric field, which creates a drift velocity. The current is known as the drift current. We will see more about drift current and also about diffusion current in our coming sessions.